Okay, here's another example. Emily is driving a car. Sorry, little typo there. Typo. It's driving a car that's a mass of 2,500 kilograms and a coefficient of friction of 0.6. So we have an object. So this is a car. We have force of gravity downwards. We have normal force upwards. So this car is not falling through the pavement. It's being supported by the road, so we know normal force is equal to force of gravity. There's also some applied force. That's that 24200 newtons. And there's some friction force that's slowing this thing down. Okay. Now, when we do these questions, you have to recognize that there's a sum of forces in both the x directions and the sum of forces in the y direction. So in the y direction, we know it's not accelerating up or down, so we know it's equal to 0. This is what tells us that the normal force is equal to the force of gravity. Okay. In the x direction, this thing does not equal 0, so we know it's going to accelerate. So I'm going to write down, so sum of the force of F net in the x direction is equal to mass times acceleration in the x direction. And we have some applied force, and it's being opposed by some force of friction. So from friction, we know that force of friction is equal to mu Fn. We also saw that Fn is equal to Fg. So force of friction is equal to mu mg, because force of gravity is equal to mass times gravity. So you get the following expression. We get ma is equal to Fa minus mu mg. So now we can just go ahead and solve for A. 2,500 kilograms times acceleration is equal to 24200 newtons minus 0.60 2,500 kilograms times 9.81 meters per second squared. Solve for A. 24200 minus 0.6 times 2,500 times 9.81, and then we're going to divide that by 2,500. We get 3.8 meters per second squared. Next question. So Emily takes her foot off the gas pedal and allows her car to coast. What is her acceleration? And so these are not the most realistic examples because in real life, cars, the wheels roll. And rolling objects actually have they follow different rules than sliding. However, because you don't actually learn the physics of rolling objects until university, we're just going to assume that cars slide. So this one, when we take off the brakes, we're no longer applying that applied force. We have force of gravity still, force normal still, those are equal and opposite, and there's force of friction. So what we can see, there's only friction that's slowing this thing down. So you have F net in the x direction is equal to ma, and that's just equal to that force of friction. So if I write this out, masses actually cancel out. Plug it in, so 0.6 multiplied by 9.81, you get 5.9 meters per second squared. So it's slowing down at a rate of 5.9 meters per second squared. For our last one, Emily slams on the brakes. So force of gravity is down, force normal is up, force friction is still in that direction, but now there's also that force of the brakes. So when I write out F net x, so it's still ma is equal to that negative force of friction, but now there's also that Fb in the same direction. So if I rearrange this equation, I get Fb is equal to negative force of friction minus ma. Fb is equal to negative mu mg minus mass times acceleration. Be careful with this one though, because acceleration is negative. Mass still 2,500 kilograms. Gravity is 9.81 meters per second squared. 2,500 kilograms. And that's going to be negative 18 meters per second squared. So when we plug all this in, so to make sure this two negatives are going to become positives, we're going to actually add that 2,500 times that 18. We get 30,285. So that's going to become 3.0 times 10 to the 4 newtons.